The KazMUQ Minerals design team was tasked with designing a copper processing plant for the KazMUQ deposit, located 220 kilometres northeast of the capital, Nur Sultan, next to the towns of Bastow and Izabilno. The mine has an estimated life of 20 years, processing at 7.85 million tonnes per annum, with the ore body being made up of 3 composites, with XFDR making up 95% of the feed. The average feed contains 3.94 weight% copper and 0.345 grams per tonne gold.
The KazMUQ ore has been identified as that of Super G mineralization, characterized by the dominance of the secondary copper sulfide minerals and virtually no chalcopyrite. The principal copper-bearing mineral, chalcocite, rims the surface of the gangue pyrite and has been shown to naturally occur in intimate association. The non-sulfide gangue is mainly composed of aluminosilicates, which heavily implies the presence of kaolinite and other clay types, which can potentially make up to 26% of the feed ore.
The processing routes investigated are shown here, with the first route containing a conventional pyrometallurgy route and the second route being a hydrometallurgy route containing atmospheric leaching and solvent extraction. The pyrometallurgy route was selected due to pyrometallurgy already being utilised in Kazakhstan, having the potential to process Bozhsha coal and neighbouring deposits concentrates, more growth opportunities to extend the life of mine, having the ability to recover gold and silver, and requiring an estimated 30% less water and 42% less electricity. The proceeding will overview each processing section.
Starting off with the comminution circuit, the crushing circuit has a feed rate of 1,195 tonnes per hour based on the maximum availability of a crusher with 75%. The grinding circuit, on the other hand, has a feed rate of 943 tonnes per hour based on this grinding circuit's availability of 95%. The stockpile acts as a buffer for this to be achieved. The main goal of the comminution circuit is to reduce the particle size to a P80 of 150 microns and a solids percentage content of 28 to 32% for the flotation feed. Different equipment were chosen for the comminution circuit. A jaw crusher was chosen as the crusher for the circuit due to its ability to match the throughput for the project, compared to that of a gyratory crusher, which is more suited for high throughputs. With the jaw crusher being chosen as a primary crusher, a scalping screen is incorporated prior to the crusher to allow work reduction by the crusher, longer lifetime for wear parts, and a lower risk of packing. With the grinding circuit, given that the ore is of medium competency and a circuit capacity of 7.85 million tonnes per year, 2 of the most applicable grinding circuits to choose from is the SABC or HPGR ball. The intrinsic properties of the ore and throughput for the SABC was the most applicable for the project compared to the HPGR ball. The HPGR ball is more suited for harder ores and higher throughputs. Overall, the circuit has a water consumption of 2,210 tonnes per hour with an overall power consumption of 13.5 megawatts. The largest contributors for electricity requirement are both the SAG and ball mill. With regards to the environmental and OHS issues, the biggest risk that's incorporated with the comminution circuit is dust. Dust production within a large comminution operation is inevitable, which can have detrimental impacts to the health of the workers, machine performance, and environment. This, however, can be mitigated with the use of water sprays to dampen the ore, which can reduce the dust generated. The usage of wet grinding will also aid in the reduction of dust generated from the grinding mills. Machine enclosure is another effective solution provided that only the dust-emitting part of the machine is encapsulated, along with the usage of a vacuum dust suppression system at key comminution equipment, which is more effective compared to water.
Following the comminution circuit, the flotation section aims to upgrade the ore, reducing an 80% passing size of 150 microns at a feed rate of 919 tonnes per hour. In particular, it aims to produce a concentrate at a copper grade of 29.84% and achieving an overall 89.22% copper recovery. The design of the flotation circuit specifically addresses the technical issues identified in the test work, namely the high pyro content, which is strongly associated with the chalcocite, liberation characteristics, as well as the clay content of the ore. Each stage is carefully designed so as to best target these issues, along with a specially designed reagent regime. Overall, the circuit is split into 2. The first part is a conventional rougher scavenger cleaner circuit with a middling through treatment through a ball mill regrind, enclosed circuit with a hydrocyclone classifier. An ultrafine circuit consisting of 3 Jamison cells using an isomill regrind is the second part of the process. The 3 Jameson cells include a scalper that produces the target copper grade, a cleaner scavenger Jameson cell to minimize gang entrainment and minimize copper cleaner losses, and a recleaner to upgrade the scavenger concentrate to the grade required for the smelter. Due to the high combination costs associated with the milling, the feed is first classified using another hydrocyclone so that only the underflow is reground by the isomill, then to prevent overgrinding. The reagent strategy involves using bulk sulfide flotation of the pyrite and chalcocite from the non-sulfide gang on the RSC circuit to maximize recovery, as well as using highly selective flotation against pyrite in the ultrafines to meet target grade with minimal copper losses. Concentrates from the recleaner and the scalper units are then sent to a dewatering stage where it will be reduced to an overall moisture of 10%. Due to the high throughput of water required for flotation, 80% of the input process water required will be sourced from reclaimed water treated that comes out of the dewatering stage for the concentrates, which is the filtering and the thickening, as well as the overflow of the tailings thickener. These tailings are then sent to an external tailings management facility.
Continuing on from flotation, we reach Area 300 of the plant, the primary smelting section. The design criteria were defined as follows. For the technical objective, a target of 60 weight% copper in the mat was chosen for 2 reasons. Firstly, it is easily treated downstream in converting, and secondly, it minimizes the copper losses to slag to eliminate slag cleaning circuit to reduce on cost and process complexity. OHSE considerations were also part of the design criteria to determine the process choice. As at KazMUQ Minerals, we do not risk injuring any of our workers or the immediate environment around us. The feed for this area of the plant was defined as the following. A high copper feed set at 29.83 weight% copper at 93.5 tons per hour. The main process routes that were considered were top submerged land smelters, flash smelters, and submerged Toyota smelting. A top submerged land smelter was chosen due to it not needing any feed drying, its fast kinetics, easily managed off-gas, and lower capital and operational costs when compared to the other technologies. An electric settling furnace was chosen to settle out the mat, taking advantage of low electricity costs in Kazakhstan. This is then tapped and ladled to Area 400. Direct blister smelting was not considered due to the initial low copper in feed and high pyrite content, leading to significant losses to the slag. A mat at 60 weight% copper and 43.35 tons per hour was calculated to be coming out of the electric mat settling furnace and to be ladled to Area 400. Major threats to this section of the plant are risks involving OHSE problems that can arise due to both off-gases, which contain 46.2 weight% sulfur dioxide, as even in small concentrations, it can be lethal to workers and the immediate environment. The off-gas is treated using a waste heat boiler to recover energy, an electrostatic precipitator to recover the dust in the off-gas, and then this is sent to the acid plant to produce sulfuric acid. A major opportunity for this section is that the smelter can handle a higher feed rate if there are third-party concentrates that are available to be processed, as well as higher arsenic ores, as this can be blended with the current arsenic-absent ore.
The processing objective of Area 400 is to further reduce iron and sulfur content and turn the 60 weight% copper mat produced from Area 300 to a copper anode for electrorefining. The feed for the secondary smelting is as follows: 59.2 weight% copper, 16 weight% iron, and 24.8 weight% sulfur, as well as minor elements, at a nominal feed rate of 46.4 tons per hour. The 2 technologies investigated for processing the mat were flash converting and Pierce-Smith converting, as these technologies make up 86% of copper converting worldwide. Ultimately, a Pierce-Smith converter was selected with the key drivers being: it's a more mature technology, it has local experts and is already being used in Kazakhstan, not requiring additional infrastructure like slag granulation, and the ability to easily adapt the equipment for third-party ores. Although Pierce-Smith converters have some challenges, namely off-gas management, this has been done by KazMUQ to safely comply with Kazakhstan's governments. The off-gas will be managed in the same way as mentioned in Area 300. The other waste stream is in the form of slag, which will be treated in a slag dam and periodically granulated by a bulldozer. There is an opportunity to recycle the slag through the concentrator. However, this will have to be looked into further. The other challenge associated with a Pierce-Smith converter is that they operate as a batch process. This will be overcome by using 3 converters, where 2 will be hot and continuously in use and the third will be re-bricked. The blister copper produced from the converter will then go into an anode furnace to oxidize the sulfur and then reduce the oxygen. The molten copper metal will be casted and produce copper anodes for further treatment.
The primary objective of the electrorefining circuit is to upgrade the copper cathodes produced from Area 400 to a saleable product. The aim is to produce copper cathodes at a fast rate whilst minimizing energy consumption and not compromising product quality. And so, the process flow sheet was developed with the following technical objectives. Produce copper cathode purity within LME grade A specification, achieve a current efficiency of 95 to 98%, thereby reducing energy where possible, operating at a high current density of 400 amps per meter squared, and minimizing the reagent and additive use. A conventional electrorefining circuit was designed whereby 503 electrolytic cells would be required. In order to size the tank house, the current density was used as the main driver. Innovative technologies and integrations within the plant were considered to develop an optimal circuit suited to the client's criteria. By implementing the MET-top box technology, the current density was increased from 300 amps per meter squared to 400 amps per meter squared. This significantly decreased the number of cells required to meet the same capacity, and therefore the footprint of the plant was significantly reduced. Additionally, the tank house was integrated with Area 300 to make use of the sulfuric acid being produced and the excess steam being produced. The analysis found that 235,000 tons per annum of LME grade A copper cathode could be produced, whereby an energy consumption of 259 kilowatt hours would be required to produce 1 ton of copper. The electrolyte bleed has been identified as a major environmental threat. This is mainly due to the handling and disposing of the electrolyte bleed, which is predominantly sulfuric acid. It is recommended to treat this bleed using an electrowinning and ion exchange circuit to extract valuables and recycling the acid back into the plant.
Moving on to the financial analysis, several key mining project components outside of the processing plant are given estimates for the capex and opex of the project. These components are primarily composed of permits, surveys, test work, pilot plant expenses, government royalties, mine capex and opex, and tailings dam capex and opex. Overall, the processing plant had a capex of 1,281 million AUD with an opex of 186 million. The processing plant can produce 3 products, which are mainly the copper cathode, copper anode slimes, and sulfuric acid. All 3 products constitute to an overall revenue of 3,215 million per annum. This then established an NPV of 4,230 million AUD and an IRR of 30% with a payback time of 6.7 years.
Has committed to designing a sustainable process in terms of social, environmental, and economics. On the social sustainability front, the plant is designed to be safe for its workers and local community. Additionally, KazMUQ Minerals will hire at least 50% local workforce, support local schools and facilities, and offer charity work to the people to bring about the health, prosperity, and longevities in the communities in which we operate. For the environmental sustainability, there are many aspects which have been considered in each individual section of the plant. The main ones that could lead to extreme environmental impact are water, energy, waste, and pollution management. In terms of water, water is supplied from a local dam, and KazMUQ will recycle as much water as practical for high-use areas of the plant. In terms of energy management, the steam coming from the waste heat boiler will be used to generate heat and energy, as well as committing to efficient designs to conserve energy.
Currently, power will be supplied by overhead lines and come from coal power, with the map signifying where the deposit is compared to the overhead lines. However,
KazMUQ Minerals is targeting net zero emissions by 2050, 10 years ahead of Kazakhstan, and will support efforts for renewable resources in the local area. Lastly, for economic sustainability, through economic analysis of the plant, designing so that there is a large enough profit margin if the prices of products fluctuate.
concluding, the KazMUQ Minerals team have designed a profitable plant that recovers 85% of the copper and will be a welcome asset to the Kazakhstan community and economy.